Okay. So under C2, the topics that we have are waves and its motion, properties of waves, and classification of the waves. Primarily, we'll focus on transverse and longitudinal, but there are a few other classification as well. We'll look into that also. Okay. So first, what is meant by the term wave? So wave is basically a disturbance that transfers energy from one place to another place. For example, if you're dropping a glass onto the floor, okay, if you drop a glass onto the floor, it creates a sound. How does it create a sound? So when the glass is being dropped, it breaks into pieces, which disturbs the air particles around it, and that air particles will transfer the energy into until your eardrum, and eardrum gets disturbed due to that air particles, and therefore you hear that sound. So that means if any wave has to travel, it requires the medium. But there are some waves that doesn't require a medium. We'll talk about that later. But yes, most of the waves, such as sound wave or rope wave or water wave, it needs a medium to transfer the energy from one place to another place. In addition to that, that needs a disturbance. Okay, so you have to first create a disturbance. And that disturbance that creates transfer the energy from one place to another place, we call that as a wave. I mean, we can't say that any disturbance is a wave. For example, if I say, I'm like talking to someone, yes, don't say that because you were disturbing someone is a wave. No, the disturbance here doesn't mean the actual meaning of disturbance. It means the vibration of the particle. If the particles are vibrating, if the medium is vibrating, that is allowing the transfer of energy to take place, we call that as a wave. And the best example you can see in the picture here. So somewhere there's a disturbance, means there is an air that blows, and that air disturbs the water particle to move forward, and therefore that carries energy until the end of this C. And that is what we called as a wave. The direction of propagation of wave is the direction of energy transfer. If I ask you in future, like what is the direction of energy transfer? It's basically the direction in which the wave is traveling, or vice versa. If I ask you what is the direction the wave is traveling, if you know the direction of energy propagation, that's the direction of energy, the wave traveling. Best example, in which direction is this wave traveling? Obviously, the wave is traveling till here and again is moving back. How do I know that? It's just based on looking at how is energy being transferred. So there are a few other examples of wave. This is a rope wave. You can see the wave is traveling to the right, means energy is propagating to the right. And this is your electromagnetic wave, light wave. I'm just representing a sound wave, and that's a water wave. Now, waves are classified based on the following categories: medium, vibration, dimensions, energy transfer. So what is if a wave needs medium, we call that wave as a mechanical wave. If wave does not need medium to propagate, we call that wave as a non-mechanical wave. Example, sound wave needs medium to propagate. Therefore, sound wave is considered to be a mechanical wave. Whereas electromagnetic wave, and also called matter wave, I mean, not also called, also there is something called matter wave, which you will learn under the unit quantum physics. So we'll leave it there. Here we'll only understand electromagnetic wave. But as an example, you can memorize there's something called matter wave, which comes under non-mechanical wave, but will not go into deep understanding what is the matter wave. For now, just leave it. We'll only focus on electromagnetic wave. So what is an electromagnetic wave? A wave that consists of both electric field and a magnetic field to it. So both electric field and magnetic field are right angle to each other. Means if electric field is traveling vertically, then the magnetic field is traveling horizontally. So this combination of having both electric field and a magnetic field, which is carrying energy from one place to another place, is called as electromagnetic wave. Fine. So what does it mean? Take an example. I have a positive charge. What does it have around it? It has electric field only around it. So can I call this as electromagnetic wave? The answer is no. If I have a magnet, okay, so it has a magnetic field around it. We know that. And the magnetic field line goes from north to south. So can I consider this field as electromagnetic field? The answer is no. It's just a magnetic field. But the combination of these two, electric field and magnetic field, is what we call as electromagnetic field. And if that electromagnetic field is transferring the energy from one place to another place, we can consider that as electromagnetic wave. So how do we produce this electromagnetic wave? For example, I'm going to take a positive charge and I'm going to make this charge to oscillate back and forth. I'm going to make it move back and forth. And this disturbance in the electric field, if I'm going to draw how is the electric field oscillating back and forth, this is how you're going to draw it. So this disturbance in the electric field is what produces the magnetic field. And that magnetic field is always have A delay of 90 degree. But so why? Why there's a delay of 90 degree? For example, if electric field is increasing, I'm leaving that part, not interested. But what is happening here? The electric field is decreasing. So that decrease in electric field is what produces the increase in magnetic field. When there is increase in electric field, that means the magnetic field should be decreasing at that point of time. And now the electric field is decreasing. That means magnetic field must be increasing. So you can see that electric field and the magnetic field has a delay of 90 degrees. And that is what we try to show drawing electric field vertically and magnetic field horizontally. It is just a better way of representing that electric field and magnetic field has a delay of 90 degrees. So because they have a delay of 90 degrees, or you can say that they both are right angle to each other, we call electromagnetic wave as a transverse wave. We'll talk about transverse wave later, but for now, you can at least remember that electromagnetic waves are transverse wave. Why they are transverse wave? Because the electric field and magnetic field are right angle to each other. Fine. So again, how do we produce electromagnetic wave? Take any charge. It need not to be positive charge. It can be a negative charge. Take any charge and oscillate it. If you oscillate any charge, it produces electromagnetic wave. As simple as that, your radio wave antennas are basically a charged rod, a normal rod where you apply an alternating current, where all the electrons inside move back and forth due to supply of this alternating current. And that oscillation of negative charge produces electromagnetic wave, which is a radio wave. But sir, wait, why it should only produce radio wave? Why can't it produce a microwave or infrared or visible wave or anything else? Now, the frequency of the wave decides what type of wave it is, right? You know that each and every electromagnetic wave spread across a different frequency. We call that spectrum, that wide distribution called spectrum. Since that distribution is for electromagnetic waves, we call that as electromagnetic spectrum. That starts from radio wave, ends with a gamma wave. How do we produce the spectrum? We put them in the order of their increasing frequency or decreasing wavelength, right? So we know that each and every wave has a unique frequency. That means the frequency of this oscillation will decide the frequency of the wave that is being generated. For example, if you want to generate a wave of frequency 10 hertz, and in that case, you need to oscillate the charged particle with a frequency of 10 hertz. So frequency of oscillation of the charged particle will decide the frequency of the wave that is being generated. So if we increase the frequency of the charged particle, it will increase the frequency of the wave which is being generated. So this is how you produce electromagnetic wave. Second, this is what is meant by electromagnetic wave. Third, why is it called transverse wave? Because there's a 90-degree phase difference between electromagnetic waves. That's all about electromagnetic wave. Now let's talk about mechanical wave, specifically sound wave. Yes. So if I have a speaker, okay, the speaker say vibrates back and forth. That's a membrane of the speaker that vibrates back and forth. And you have air particles with no disturbance now. No sound is being produced. All the air particles are at rest. But as soon as I produce a sound, means this membrane will be pushed outward, will push this air particles to the right, and these air particles will go and hit the second layer of air particles, which makes second layer of air particles to the move to the right. And when the first layer of air particles been hit by the second layer of air particles, those air particles will bounce back. Means while the second layer of air particles are moving to the right, meanwhile, the first layer of air particles are bouncing back. They're moving back, which means each and every air particles are oscillating right, left. So this oscillation is what carries the energy through the air particles, and we call this wave as a sound wave. So we understand that the sound wave can only propagate with the oscillation of air particles. Just imagine you remove the air particles. Can sound wave propagate? The answer is no, because if there is no air particles, your eardrum will not be vibrated. And if your eardrums won't vibrate, there won't be any signal that will be transferred to your brain. So sound wave is possible with the oscillation of air particles. Hence, sound wave is a mechanical wave. So more we'll talk about sound waves and all later. Let's move on with classification. Yes, second classification is based on how the particles are vibrating. If particles vibrate perpendicular to the direction of propagation of wave, we call that wave as a transverse wave. And if the particles are vibrating parallel to the propagation of wave, we call that wave as a longitudinal wave. So let me show you an example. Yeah, look at this example here. Just focus on one of the particle because all the particles together may create an illusion and you feel like all particles are moving to the right. It's just the illusion. No particles are moving to the right. They're just oscillating right and left. Let's fix one of the particles, that's red one, and see how is it oscillating. It's just moving right, left. And in which direction is the wave propagating? To the right. So, but wait, how did you decide the wave is propagating to the right? Don't forget, clearly said, the direction of energy transfer is the direction of wave propagation. Since all the energy is carried to the right side, the wave is propagating to the right. And what is the angle between the wave propagation and the medium vibration? They are parallel to each other. Therefore, sound wave is considered to be longitudinal wave. I repeat, longitudinal wave is a wave in which the medium vibrates parallel to the wave propagation. Therefore, sound wave is an example of longitudinal wave. What about transverse wave? Look at this one. Yeah. This is the rope wave. Particles are moving up and down. In which direction is the wave propagating? To the right. Look at this example here. How are the particles moving? This is moved up. They're moving up. Look at this. This particle is moving up. Look at this particle here. Moved up, now down. Up, now moving down. Yes, so the particle in this rope is moving up and down. But how is the wave propagating? It's clearly visible that the wave is propagating to the right. So what is the angle between the particle vibration, which is up and down, and the wave direction that is to the right? They're right angle. Therefore, this type of wave is called as transverse wave. So rope wave is an example of a transverse wave. Yeah, so that's the difference between transverse wave and a longitudinal wave. Repeating again, transverse wave in which the medium vibrate perpendicular to the wave direction. Longitudinal wave, the wave in which the medium vibrates parallel to the wave direction. Okay, next. Next classification is based on dimension. If the wave requires only one dimension, or not just require, I would say, it's better to say like this. If a wave travel in one dimension, we call that wave as a one-dimensional wave. If the wave travels in two-dimensional plane, we say it as a two-dimensional wave, and if the wave travels in a three-dimensional space, we call that wave as a three-dimensional wave. For example, you see a rope wave. In which direction the rope wave travel? So it might be traveling to the right, or maybe traveling to the left, or maybe traveling to the down or up. That means it is just using one dimension. It just travels only in one direction, nowhere else. So rope wave is an example of one-dimensional wave. What about a water wave? Take an example. This is a water tank. You drop a stone here, and you see a ripples created like this. Yes. So in which direction is the wave traveling? Here, 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 everywhere along the surface, right? Everywhere along the surface means along the y direction, or you can call this as x direction, and this as the y direction. So two-dimensional wave because it is traveling along two dimensions. And finally, sound wave. So if this is your room and you have a speaker in the corner of the room, this is a speaker here. So if you're standing, if person one is standing here, person two is up here, person three is a corner in this room. Each and every person in this room will be able to hear the music. That means the sound wave is traveling along x direction, along y direction, and along also z direction. So since the sound wave travels along all the three dimensions of the room, therefore it considered as a three-dimensional wave. Next, classification is based on whether the energy is being transferred or not. Look at this picture here. You can see there's a torchlight. The torchlight is sending out the white wave, which consists of V, I, B, G, Y, O, R, and that is traveling here and is coming out as a rainbow, whatever. Now here it started, and here it is ended up. So wave is traveling. It seems you see the direction, you see that the energy is propagating. The energy is traveling in one direction. And if you find energy transfer to take place, we call that wave as a, sorry, if you see the energy transfer to take place, we call that wave as a progressive wave. And if you see no energy transfer to take place, we call that wave as a stationary wave, also known as standing wave. Example of a standing wave is a guitar string. So what happens? If this is the two boundaries of the guitar string with no vibration, it is like that. And as soon as you give a stroke, the string vibrate, maybe go up and it again come back down like this. And again it go up and then come back down like this. If I ask you which direction is the wave traveling, you will not be able to say that. I'll show you. I'll show you one picture. Look at this picture. You see the mediums, each and every particle in the medium is vibrating. Maybe few of them are not, but mostly all. And if I ask you what is the direction the wave is propagating, to the right or to the left, you cannot say that. Yes. And this type of wave is called as standing wave because they seems to be standing. They're actually moving. Why they are actually appear to be standing when, sir, you're saying it is moving? It's too early to learn about that because we have a separate chapter on standing wave. We'll learn about standing wave in depth there. For now, the only thing you need to know is that if a wave appears to be standing, not moving anywhere, it is called standing wave. And if a wave appears to be moving, for example, this one, you can see it's moving, like let the wave pulse to be created, or maybe, yeah, this one. You can see it's moving to the right. Transverse wave, sorry, progressive wave, right? It is traveling wave, progressive wave. You see it is traveling in one direction. But whereas in this case, you cannot say in which direction is the wave traveling. Now, don't say, sir, it is vibrating up and down. So how can you say it is not traveling? I'm not talking about the medium vibration. I'm talking about the wave propagation. In which direction is the wave propagating? You can't say either it is to the right or to the left. Therefore, this type of wave is called as standing wave. Next, properties of the wave. So first property of the wave is a wavelength. It is basically the distance between two consecutive points on a wave that are in phase. So what do you mean by the point in phase? So take an example. If this is a ferry or go around, whatever you say. So there are four chairs, one, two, three, and four. This is you. Your friend A is sitting here, friend B is sitting here, friend C is sitting here, and friend D is sitting here. So friend A is exactly standing in front of you. If I ask you at what angle he is standing, your answer is going to be 0 degree. Whereas a friend B is standing at an angular distance, means how far means you can say either in terms of distance or in terms of quarter of a circle or in terms of angle. How far is he in terms of angle? Your answer will be 90 degree. So B is at a distance of angular distance of 90 degree, whereas C is at an angular distance of 180 degree, whereas a D is at an angular distance of 270 degree, right? Now, any point which is at a distance of 0 degree or 360 degree. Why is it 360 degree? Because don't forget, A can also be said to be standing at a distance of 360 degree away from you. Because 0 degree and 360 degree are the same point. So if any point is at an angular distance of 0 degree or 360 degree, are said to be in phase. And if any point which is at a distance of 180 degree is said to be out of phase. Clear? So we understood the meaning of in phase and out of phase. Now let's talk in terms of wave now. So this is the wave drawn, a transverse wave drawn. You know, this point is said to be at an angle of 90 degree. You know, sinusoidal angle. It's a sinusoidal wave. This point is at 90 degree. And this point is at 360 plus 90, which is going to be how much? 450. So what is the angular difference between point A and point B? So you'll do this 450 minus 90, which is 360. So as I said very clearly, any point which is having angular difference of 0 degree or 360 are said to be in phase. So A and B are 2 points which are in phase. So what about any other point on the wave? For example, I'm taking this point here, which is at an angle of 180 degree. What about this point here? No, it's not 180 degree. I should say 360 plus 180, which is going to be 360 plus 80 is 460. 460 plus 80 is going to be 540. Yeah. So this point is at 540 degree. So what is the angular difference between the point C and the point D here? So angular difference between the point C and point D will again be 360 degree. So therefore, point C and point D are also set to be in phase. Now we'll take any other point. So I'm going to take this point, which is making an angle of 90 degree. And going to take this point. We'll call this point as E. At what point angle this point is? E. It is at 270 degree. So what is the angular difference between this point A and point E? It is 270 minus 90, which is 180 degree. Therefore, point A and point E are set to be in out of phase. So I hope that's clear that what do you mean by the term in phase and out of phase. So redefining it, let's read this again. What is a wavelength? So wavelength is nothing but a distance between 2 points in a wave that are in phase. So you can consider these 2 points which are in phase. You consider these 2 points which are in phase. You consider these 2 points which are in phase. You consider these 2 points which are in phase. That distance between those 2 points which are in phase is called wavelength. Okay, I mean, you must have learned in lower grade that distance between two consecutive crests or distance between two consecutive troughs is called wavelength. But are, I mean, is it only just crest to trough to trough? No, it can be between any 2 points, maybe this point to that point, or this point to that point. So any distance between any two consecutive points that are in phase is called wavelength. That's it. Now, what is amplitude? It is maximum displacement of any particle in a medium. For example, I have a rope like this, and I've started creating a rope wave by making the particle on the extreme end go up and down. So this is how the rope wave is created. So you can see this particle has gone up by this much displacement. That's the maximum displacement. That's the maximum it can go. And that maximum displacement from the equilibrium is called as amplitude. In simple terms, how far the particle can go from the equilibrium is called amplitude, denoted with the letter capital A. Next, wave height. So wave height is twice the amplitude. So if I draw a transverse wave like this, so from crest to the trough, from the peak to the valley, that's basically twice the amplitude, which is called as wave height. Frequency. It is the number of vibrations made per second, or number of oscillations per second is called as frequency. Time period. It is nothing but the time taken by one oscillation or time taken by one wave, time taken by one complete oscillation is called time period. And also time period is reciprocal to frequency. Finally, wave speed. So as any other speed, which is called product of distance and time, wave speed is also product of distance and time. Let's take, if this is a wave, if I ask you what is the speed with which this wave is traveling, so you will ask, what is the distance traveled by one wave and what is the time taken by this one wave? So we know the distance traveled by this one wave is its wavelength, and the time taken by this one wave is called its time period. So which is wavelength into its time period is your wave speed. And we know that time period and frequency are reciprocal. Wait, I wrote a wrong formula for speed. So speed is distance by time. Since speed is distance over time, so distance traveled by one wave is its wavelength, and time taken by one wave is its time period. Therefore, V is equals to lambda over T. And 1 over T is frequency, so therefore we can written as lambda into F. That's the formula for wave speed. Now, before we start solving the problem, one thing to be noted down that we are dealing with both transverse wave and longitudinal wave. So transverse wave has what? It has peak, which is crests, and valleys that are said to be troughs. Whereas a longitudinal wave has compressions and rarefactions. Compressions and rarefactions. So what do you mean by compressions? Compressions are the region where the density is high or where particles are very close. Particles are close together. What about rarefaction? This region is rarefaction, not rarefaction or rarefaction, like reflection or refraction. No, it's rarefaction, okay? So don't get confused with refraction and rarefaction. Refraction is like a wave traveling from one medium to another medium. Whereas a rarefaction is a region where density is low. Density is low or particles are spread apart. For example, let's go through the picture here. The sound wave, Jeff. So you can see there are regions here where particles are very close together, and there are regions in the between two consecutive compressions, a region where there are particles are very spread apart, right? There is a low density region. So this is your high density region where particles are close together, and this is your low density region in between where particles are spread apart. So this is your compression, and that is your rarefaction. For example, look at this picture here, compressions and at rarefaction. Again, this region is compression, and this region where particles are spread apart is your rarefaction. Okay, this is how we draw diagram in the exam with compression shown with lines drawn closer, rarefaction shown with line drawn further apart. So that is how we draw transverse wave, and this is your transverse wave, and this is your longitudinal wave. But when I put these two waves mathematically, like if I want to draw these two waves mathematically, how do we draw it? Means I have a rope wave, I have a sound wave. I want to draw them on a displacement versus displacement graph. How do I draw it? So this position is zero, say this position is 10 centimeter, 20 centimeter, 30 centimeter, and 40 centimeter. So I'll put it 0, 10, 20, 30, 40. So the particle at 0 centimeter has how much displacement? Nothing, 0. But the particle at 5 centimeter has how much displacement? Maximum going up. So how much going up? Maybe it has gone up by say 3 centimeter. So particle at 5 centimeter, particle which is sitting at 5 centimeter has gone up by 3 centimeter. So that's going to be the point. Next particle at 10, 0. Particle at 15 has gone down by 3 centimeter. 20 again 0. 25 again gone up by 3 centimeter. 30 0. 35 again gone down by 3 centimeter. 40 0. So joining these 2 points, that's a mathematical representation of a transverse wave. So wait, isn't mathematical representative of a transverse wave and the actual transverse wave looks same? Good, it looks same, but they're not same because this is the actual wave and this is just a mathematical representation of that wave. Now we'll draw displacement versus displacement graph of this longitudinal wave. How do we draw it? So let's say if I start from this being 0, this being here 10 centimeter, and this being here 20. So 0, assuming all the particles move to the right, the particles move to the right means positive, the particles move to the right until this point, may say 3 centimeter, until 3 centimeters, particles move to the right. And then from 3 to this, say 7 centimeters, particles were moving to the left. So this is your positive region, means right. From 7 to 10, this is your 7 to 10. All the particles have moved to the left, represented by negative peak. And say again 10 to say 15, all particles were moving to the right, so positive, 10 to 15. And 15, 20, all particles will move to the left. So with a negative. So what I'm trying to draw, I'm trying to show you all that since longitudinal waves either move to the right or to the left, if right sides were represented with a positive peak on the mathematical graph, then left side should be represented with a negative peak on the mathematical graph. And what you observe is that mathematical graph looks like a transverse wave. Now, don't consider it as a transverse wave. No, the transverse wave is not defined by how the mathematical graph look like, because both the graph looks like a transverse wave. No, we don't define a transverse wave or longitudinal wave by looking at the mathematical graph. We define whether they are transverse wave or longitudinal wave depends on how the particles are vibrating according with respect to the wave direction. Okay? So if that is clear, then let's move to the numericals. I'm skipping this. You can try it on your own. Numericals such as this. The diagram shows 3 points on a string on which a transverse wave propagates to the right. So here it says that the transverse wave is propagating to the right. Indicate how these 3 points will move in the next instant of time. How these points will move in the next instant of time. We think this particle is moving up, appears to be moving up. I mean, we think these particles will move nowhere. That's an assumption. We'll see whether that's actually true or not. How do you solve it? Since it is said that the particle is moving to the right, you draw another wave at the next instant of time, like that. So why are you drawing to the right side? Because wave is propagating to the right. Now, no longer this wave exists. This is your wave now, because it has moved to the right. It has displaced to the right. So this point will no longer there. It will be dropped down to the new position of the wave. This point will no longer be there. It will drop down to the new position of the wave. This will be dropped down to the new position of the wave. So how is this particle 1 moved downward? Particle 1 moved down. Particle 2 also moved down, whereas particle 3 has moved up. So this is how you say that these 3 points will move in the next instant of time. The next question is, how would your answer change if the wave were moving to the left? So now you will draw a wave displaced to the left like this. You're going to displace the wave to the left and just draw it. How much should I displace it to the left? Any amount is fine, but don't draw a huge, like if this is your wave, you don't draw another wave by this much distance. No, just a little distance far away. So if this was your old position of the particle, drop it onto the new position. This onto the new position of the wave. This onto the new position of the wave. So particle 1 has gone up. Particle 2 also has gone up. Particle 3 has gone down. Now, the diagram shows a piece of cork floating on the surface of the water when a water wave travels through the water to the right. Copy the diagram and add to the position of the cork half a wave period later. So this time not a next instant of time as they said before. This is a half a wave period later. So you will draw half a wave period later. See, look at this. I've drawn a wave, half a wave period later. That's half a wave, right? And you can just extend it to finish the complete wave like this. Now, the question is, what will be the position of the cork after half a wave period later? So this was initial position. Now it will be dropped into the new position. That's the new position of the wave. Therefore, we can say that the cork will be moved downward. The cork will be moving downward. That's it. Next question. Calculate the wavelength of the wave that correspond to the frequency of this. I'll just solve for first one. So wavelength can be calculated by using the formula V is equal to lambda into F. So lambda can be written as V over F. What is the V given? Speed of sound, 330 meters per second. F is given as 256 hertz. Simplifying this will give you the answer. Next. This is important. The graph shows the displacement y of the particle in a medium against position x when a longitudinal wave pulse travels through the medium from left to right. Okay, so underline. What are things to be underlined? First, it's a longitudinal wave. Second, it is traveling to the right. So if it is traveling to the right, which is represented with a positive peak, that means traveling to the left would be represented with a negative peak. Understandable. That's what I said. So, but this wave looks like a transverse wave. But they're saying long because it's a mathematical graph. It's a graph. It's a graphical representation of a longitudinal wave. But in reality, particles would be, all the particles would be until here from 0 to 4 would have moved to the right. And particles from 4 to 8 all would have moved to the left. Like that. That's how you draw it. Okay, so let's continue. State what is meant by longitudinal wave pulse. So longitudinal wave pulse is a pulse in which the particles move parallel to the wave direction. Next. The diagram shows a line of 9 molecules separated by 1 centimeter. The position shown are the equilibrium position of the molecules when no wave travels in the medium. You can see 0, 1, 2, 3, 4, 5, 6, 7, 8. They all are equilibrium position because the wave is not traveling anymore. But copy the diagram immediately below the copied line. Draw another line to show the position of these molecules when the wave pulse travels through the medium at time t0. I'm going to draw another line below it on the same graph. And we'll show how these particles 0, 1, 2, 3, 4, 5, 6, 7, 8 would be moving when time t0. So going back, when time t0, this is the peak. That's it clearly said. When time t0, this is the peak. How much the particle 0 has moved? Nothing. So particle 0 will remain as 0. So I'll draw it as 0 dash. Will stay there only. Next, how much particle 1 has moved? It has moved by 1, 2, 3, 4, like point 0.05, point 1, point 0.15, point 2, point 0.25, point 3, point 0.35. It has gone by 0.35 centimeter to the right. 0.35 centimeter to the right. So 1 dash will go here. Why right? Because positive. We're dealing with positive peak. What about the particle at 2? It will go zero point 0.5, 0.55, 0.6, 0.65, 0.7, 0.75, which means higher than particle 1. Higher than particle 1. So that's why you can see particle 2 dash has gone right by higher amount compared to 1. Whereas the particle 3 would be moving same amount as the particle 1 to the right. Particle 3 would be moving same amount as particle 1 to the right. Whereas the particle 4 has gone nowhere. Particle 4 has gone nowhere. Particle 5 has gone down as much as particle 3 and particle 1, but to the left. Particle 5 has gone as much as particle 3 and particle 1, but to the left. Whereas the particle 6 has gone left as much as particle 2. Particle 6 has gone to the left as much as particle 2. Whereas the particle 7 has gone left as much as particle 5. And finally, particle 8 has gone nowhere. It stays there. Now, so done. We have drawn the particles. This is how the particles will be when the wave travels through the medium at time t0. Indicate on the diagram the position of compression. So you know the position of compression is nothing but a region where particles are too close apart. So this is completely a compression because all the particles have come closer. But you can't say compression means overall. You have to always select the mean of it. So mean is 4. So we can say the compression is at 4. Compression is at 4. Next, repeat B1 to show the position of these molecules at time t equals to 1 second. Now, when time t is equal to 1 second. So at 1 second, the wave peak will not be same as here because the wave is traveling to the right with the speed of 1 centimeters per second. That means wave would have displaced itself by 1 centimeter. So this goes like this. So it starts from here. Peak will end at 3. Another will go down at 5. Peak will be ending at here, and another will be joining this two point. This is how my peak will be. So this is how my wave pulse be. So from 0 until 1, the particles have 0 displacements. From 0 until particle 1, particles have 0 displacement. Right? So let me draw. 0 goes nowhere. Particle 1 also go nowhere. So, but why? Because look at it. It was a straight line here. So when the wave is going to the right, the straight line will also be moved to the right. Particle, particles from 0 to 1 has a 0 displacement. Means it is going nowhere. But what about particle 2? It has gone to the right by this much amount. Particle 2 has gone to the right by this much amount. So, but wait, you're just drawing roughly. You're not showing how much accurately. Not required. They just said, just show the position. You don't need to be very, very accurate. But in case if they say use proper scale, then you have to draw with the ruler, but otherwise not required. Whereas particle 3 has gone higher displacement to the right than 2. So particle 3 will be going under there. Whereas a particle 4 has gone as much as particle 2 to the right. Particle 5 has gone to the left. Sorry, particle 5 is 0. I'm sorry, particle 5 is 0. It's not going because that's the wave, new wave, no? Particle 5 is going nowhere. That's 4 dash, 5 dash. Particle 6 is going, sorry, particle 6 is going this much as particle 4, but to the left. As much as particle 4, but to the left. Whereas particle 7 is going extreme left as much as particle 3. Whereas finally particle 8 is also going to the left as much as particle 6. Done. That's how each and every particle will be. 1 dash will be here, 2 dash will be here, 3 dash will be here, 4 dash will be here, 5 dash, 6 dash, 7 dash, and 8 dash. Comment on the position of compression at 1 equals 1 second. Where is the compression now? You can see all the particles have come closer and here. So now the compression is also shifted by 1 centimeter. Now it is at 5 centimeter. That's the compression region. The main position of the compression is a compressed region, a position. So that's about the topic C2. In the next class, we'll go with C3.